In this video, we are going to cover linear time. And this is the time complexity we think about whenever we see a for loop. We think of, hey, I'm gonna do however many iterations that my guard is going to allow me. The problem is this becomes trickier when we have nested loops, when we're dealing with more complex algorithms like heap sort. The build step of building the max heap out of the unsorted array in heap sort runs in linear time with an exact bound. That's a more confusing case of linear time, but we're just gonna see common cases we might see linear time and what it means. First of all, I really want to drill this in. Never assume the time complexity by looking at the code and just guessing. It's a very bad idea because in an interview, you're going to be asked why. And if you can't explain why, it just puts you in a tough situation. It's really important that you figure out exactly what the runtime of the code is. And this is much trickier with recursive algorithms because the math becomes much trickier. We have to deal with summations and we have to do a lot of calculation. Most of the time with interview questions, finding the time complexity won't require math. You can just eyeball the code and know what's happening. For this, first I want to introduce to you a common bound, which is big O of m plus n. This is still called linear time, but it's actually a special kind of function called a multilinear function. So let me write what I'm saying. We see this bound sometimes when we're dealing with, maybe we have an m by n matrix and we only do as far as the width, the columns, and as tall as the rows in terms of time with some constant. We might have a constant in front of this. But the upper bound on the work we do is the width plus the height. And we can multiply whatever we want. It'll go away with the asymptotic bound. What this is equivalent to saying is, it's equivalent to saying this. The upper bound of max m comma n. Whichever is the maximum is what's going to dominate and ultimately be what parameterizes this upper bounding. So why is this the case? So let's look at a quick derivation and see what this really means so we can get a deeper understanding of what's going on with these multilinear bounds. So if we have max m comma n, we know for sure that that is going to be less than m plus n. And the reason is, if one of these guys wins, the winner is going to lose to the sum of the two items. So let me finish off this statement. So let's imagine m is bigger. If m is bigger, we're going to compete that against m plus n. If I have m versus m plus another item, we're always going to lose or be equal to if n is 0. If n is 0, this is the equivalent of saying m is less than or equal to m. If m is the winner here with the max. What this means is that m plus n serves as an effective f of n function to bound this guy. So what happens is we can say max of m comma n is bounded by m plus n. So this exact amount of work, which is either m or it's n, whichever is bigger, is upper bounded by this multilinear function, big O m plus n. We see that this provides an upper bound for that. But now let's go the other way. If we have m plus n on the left side, this is going to be upper bounded by some arbitrary multiple of max m comma n. Let me show you. So if we look at the statement and see what it's saying is, we're saying the exact function, the m plus n, is bounded by this function 2 times the winner of both of these guys. So if m is bigger, then we're going to say 2 times m. How does that compete against this? It's going to beat it because if m is the bigger guy, n is either equal to or smaller. So that allows us to say that this is going to be less because I'm competing 2 times the bigger guy against the bigger guy plus whatever n is. It might be equivalent, it might be less. This holds. And what we understand about our upper bound is it removes the constant. So we can say that this m plus n is bounded by max m comma n. Because we see that this upper bounds this, and in the previous case, we saw that big O of m plus n upper bounded this exact quantity, we see that these bounds are actually saying the exact same thing in terms of asymptotic complexity. They're describing the same set of behaviors. These are both linear functions. They're just parameterized by 2 items, and they're going to both look like lines. If you actually looked at the concrete functions themselves, they're different. different. They're different functions. But when we look at what they're saying, when we apply a bound to them, they're actually saying the same thing. They're both a testament to a linear behavior. They're both a testament to a line going infinitely far as the input becomes very large. It scales linearly. They're a testament to the same behavior. This is kind of drilling in originally what I was saying about the exact derivations may be different, but when we bound something, we start to see there are classes of behaviors. There are classes of behaviors behind these functions themselves that lead to equivalences, and this is what allows us to understand runtimes better because we know that these two functions behave nearly the same on the tail end. Or the same, basically, since it's linear. I just wanted to get that out of the way because that's a complexity we see sometimes. Another statement that I want to make about linear time is as long as we're not nesting operations, as long as we're not doing multiple passes that depend on another variable, it will stay to linear time. So if I do a pass over the whole array, and then I do a pass over half of the array, and then I do another pass that is over the whole array, I'm still going to have done 2.5 passes, and that's removing the constant still linear time. For certain questions, we are presented with the option of doing more passes to save space, but often we don't want to save space because space is something we can always make more of, but we can't make more of time. So often it's better to save ourselves time and favor using more space. Although it's hard to optimize beyond this because they're just straight passes. We only could go down to log n or constant time. So now let's look at an example of a problem that we can solve with less space and actually stay to linear time. So let's put an array here. So we're given this array, and what the question is we want to partition the array so we have two sections, a section of even numbers, a section of odd numbers. Evens first, odds second. Whenever we're dealing with an array problem, we almost never want to create another array. When we're dealing with a linked list problem, we almost never want to create another linked list. We want to reuse linked list nodes. We want to stay within the bounds of the array. And often, we use swaps. Swaps are a very common thing with interview questions within the array. In partitioning, we know in quicksort, we swap. So we're going to execute swaps here to keep us from creating another array and using O of n space. Before we even start the problem, we need to observe what is the work that's already finished for us. And since evens are at the beginning and odds are later, we know that even numbers are possibly at this beginning. And we don't need to move anything if evens are already here, and we need to just focus on getting odds to the end. Because if we have even and odd numbers, we know that if all the evens are at the front of the array, the only possibility for all the other items that we throw to the back is going to be odd numbers. Because of parity, we know that there's only two possible situations. And this is different for things like the Dutch national flag problem. We partition into 3 sections, and then we would do 2 passes, one forward, one back. But the concept is the same. So we'll go over other problems like that, dealing with partitioning. We see that in quicksort. We see that in many other algorithms. So what we need to do is we need to work within the array. And what we can do is we can use a pointer approach to do so. And we can put a pointer here to place evens. We know we want even numbers to be at the front. And we can place another pointer at the end for odd numbers. We know we want odd numbers at the back. These are just placement pointers. This is a very common concept. You might find this useful for other problems where you want to stay within the structure. So what we're going to do is we're going to prioritize the front. We could do it from the back. We could do it from the front. Either way, we see, is this number even? Well, it's not even, so let's move it to the back. Swap this item with what's at the back and move the odd pointer this way because we just placed an odd item over where the odd pointer is. So swap to perform a placement. So what we just did is we swapped the 89 into 90's place, and now we just placed an odd item, move the odd pointer this way. And so again, we look at the even item. Since this item is even, or we look at the even pointer. Since this item is even, we just move forward. We already placed an even item. For the next check, we see that this item is not even. So swap it to where the odd pointer is, move the odd pointer back one because it just got what it wants. It got the odd item. And now, again, what we do is look at the even pointer. Is that even or odd? Again, we have an odd item. So throw it back to the odd number. Throw it back to the odd pointer. And we swap 89 and 72. And the odd pointer just got what it wanted. It got an item that's odd to the back. And again, we're not worried about sorting, we're just partitioning. Order of the items does not matter, the properties of the items matter. Again, look at the even pointer. Is that item even? Yes. Advance forward. And then we see 30. We're, again, prioritizing the even pointer. We could have prioritized the odd pointer. It doesn't really matter. We prioritize the even pointer. So what we do is 30 is fine. Move even forward. And now our pointers are overlapping. What this is signifying is we know everything behind the even pointer is definitely even. We know everything behind the odd pointer is definitely odd. So whether that middle item is even or odd, it doesn't really matter. It's either going to fit into this even section or it's going to fit into the odd section. It's fitting into whatever section of the sandwich it belongs in. And again, I say sandwich in the quicksort partitioning scheme as well. That's a good way of thinking about this. These are sections of the array. What we've done is, effectively, we've done n operations. All we've done is array reads. All we've done is swaps. And in these swaps, we're doing array writes with a temp variable. These are all constant time operations. And we've done n of them, or I think roughly n. So that leads us to a linear time bound. This operates in linear time. As this array gets huge, we're going to have a steady linear graph representing the time it takes to process this. So again, like I was saying before, we see linear time appear in the build heap phase of heap sort. In the first phase of heap sort, we start at the middle of the array, and then we go backwards and we build out a max heap. Or it could be a min heap, whichever way you want to place the items into the array. But we build the array into a conceptual heap. And what we do is we perform logarithmic removals later. But ultimately what is happening is in that first phase, we do a linear amount of work. And the only way to understand this, you can't just look at the operations and assume this, you have to do the actual math. And that video is covered in my heap sort video. I'm going to leave it to that video, but I just want you to be aware there's odder instances of linear time occurring. Ultimately, what it means is the growth of the work is a steady line. So let's review what we have learned about linear time in this video. So we learned that linear time is often seen when we're dealing with linear data structures like arrays and linked lists. We also know that if we do multiple passes of the array that are not dependent on a nested loop, if it's not a nested loop, if it's just regular multiple passes over the array, we're going to stick to some multiple of the array. It doesn't matter if we do a fractional pass or a full pass. It's always going to be a constant we can rip off, and it's just going to become O of n. What we also saw is how we can achieve linear time in constant space without creating another array or other linear data structure. We can stay within the array using pointers, and this becomes very useful in many array questions. Many array questions, you can just play within the array, use pointer, and swaps to achieve the partitioning or the constraints that you're asked to achieve. Finally, we saw how linear time can appear in odd cases where you can't really know the time complexity unless you do the actual math. This is in things like heap sort, and I have a video for that. You can check that as well. We've covered constant time, we covered logarithmic time, we've covered linear time. Next, we need to look at another bound we see sometimes, and that is the bound of n log n. And that's what we're going to look at next.